All right, grade 12, after introducing batteries and a little bit of circuits and the idea about voltage and electrical potential, we talked a lot about putting a battery up to a wire and creating a current. Okay, the formal positive current is going in that direction. The electrons are going in the opposite direction. So what exactly causes that? Well, that's because the battery is creating an electric field inside of that wire, and that electric field is causing a force on charges to move. Okay, so normally these charges would want to come back and balance out as quickly as possible. However, they can't, and different materials that we put into that wire are going to affect how fast those charges are going to flow. So the impedance of that, or the slowing down of that charge to flow, is called resistance. So this lecture here is going to be a little bit about introducing to the concept of electrical resistance, which is very, very important in circuits. Okay, so the objectives for this is, first, you're going to understand how a current in a circuit generates thermal energy. That was really important when people were first studying it. Why is heat created when I put a battery up to a wire? Okay, then we're going to understand the actual term, what is resistance, electrical resistance, and how it relates to something called Ohm's law. That we'll get to by the end of the lesson here. Okay, and then we're going to learn how to calculate the resistivity, which is an actual physical property of materials, a physical property such as specific heat capacity and other things that we've looked at. We can measure the electrical resistivity of different types of metals, of conductors, using simple experiments. Okay, so let's get going. So I don't know if you've seen Jurassic Park. This is one of my favorite movies. And this kid's climbing an electric fence, and all of a sudden it turns on, and he flies off, okay, gets zapped, and he dies for a second, and then they revive him, and you can see his hair is all burnt, his hands are all burnt. So ask us the question, why do we get burns from electrical circuits? Well, first of all, we need to understand the nature of the voltage. Voltage, electrical potential, is a measure of energy per coulomb. It's the work that we had to do to put charges into this space of a battery. Okay, so it's storing energy. Okay, then current is the number of electrons that are flowing per second, or coulombs flowing per second. Okay, so when we have current flowing through the wire, there's a number of charges flowing through, and those charges are releasing energy per coulomb that is flowing through. So where does that energy go? Okay, does it just disappear? Well, it goes to do work against resistance, the resistance of the atoms inside of that wire. Okay, and as that current flies through, if I have a very large current and a very large voltage, such as that in this wire over here, that's a high voltage wire, you're going to get a lot of joules of energy released in 1 second. A lot of joules in 1 second. Okay, and those joules are going to go to the atoms in the wire, making them move around and raise their temperature quite rapidly. Okay, so his hands are going to get burnt because the wire is going to get really, really hot. And on top of it, if the current flows through him, his atoms are going to move a lot and he's going to get really hot. Okay, so in summary, wires get hot. We get burns from circuits because of voltage, current, and resistance. Those are the three things that we need to understand. Okay, so what is electrical resistance? Because we know what voltage and current is. Well, electrical resistance is the impedance of flow of charge. Okay, that's how I'd describe it, but there's a special definition for it. So whenever a potential difference is applied to a conductor, so for example, let's get a different color here. So for example, if I apply a positive plate over here and a negative plate over here, and I attach it to those sides of that conductor, okay, I am going to generate a very strong electric field. Okay, I'm going to generate an electric field across that conductor. Okay, and let's say that potential difference across those plates is, let's say, 1,000 volts. Okay, so that 1,000 volts and the distance separating those plates is going to create an electric field, which is going to cause charges to move. All right, now there's a force for those charges to move, and if this was a vacuum, those charges would move freely. But there's atoms and stuff in the way, so they're going to impede the flow. Those charges are going to have to bump around those atoms and flow across the plates. So the rate of charge movement is different and depends on properties of the materials. Some materials have really tightly packed atoms. Some materials are quite loose and allow charge to flow really easily. Okay, and their ability to slow down the charge is called electrical resistance. Okay, and if I really wanted to define what electrical resistance is, I would use a formula called Ohm's law. okay, which states that electrical resistance of a conductor is defined as the ratio of applied potential to the current flowing through a conductor at a constant temperature. And that's called Ohm's law, okay? A definition that you need to know, okay? So Ohm's law states that the resistance of any conductor is the ratio of the voltage that you apply to the current that flows through it, okay? The smaller the current and the higher the voltage, the higher the resistance. Okay, that makes sense. I got a very strong electric field and very low current. I have a very high resistance in that material. Okay, and ultimately we want materials that have low resistance. Okay, gold, for example, has very low resistance if I'm using it for an electrical conductor. Okay, so R is resistance, and that's measured in ohms, which has a symbol that looks like omega. Okay, that's the symbol for ohms. Okay, electric voltage is the electrical potential measured in volts, which has a symbol of V, and electrical current is measured in amperes, which has a symbol of A. Okay, in your textbook, you'll be able to see that. And it's very simple. So let's do a quick sample calculation. If I had a wire that passes a current of 2 amperes when a potential difference of 4 volts is applied, such as in the circuit, okay, in this circuit, that's the positive, that's the negative, that's my battery, and it has a 4-volt battery. To make sure it has 4 volts, I connected something called a voltmeter, which we're going to learn a little bit about in the next video. But a voltmeter I can put on either side, either ends of the wire to measure the potential difference across the wire, and it tells me 4 volts. Okay, now to measure the current flowing through, I have to count the number of charges that flow by every second, and that's called a device, an ammeter. Okay, an ammeter is a device that counts the number of charges that flows through per second. And that device is telling me that 2 amperes or 2 coulombs of charge are flowing through per second. So 2 coulombs per second is flowing past that point, okay? So now how would I use that to calculate resistance? Well, resistance is equal to voltage divided by current. So the resistance is equal to 4 volts divided by 2 amperes, which is going to be equal to 2 ohms, okay? So this wire, the whole wire has 2 ohms of resistance. Okay, we've calculated that. Okay, that's what's impeding the flow of charge. Okay, and the flow of charge would be positive charge flowing in that direction, which is my formal current. Okay, that's the way things go. So we calculated 2 ohms of resistance. Now, all materials have different resistivities. That's not resistance. Resistivity is a property that resists the flow of electrons in a conductor. So if I'm looking at gold, I'm looking at silver, I'm looking at bronze, I'm looking at graphite, they all have different resistivities. You know, I mean, which one do you think would resist the flow of electrons more, graphite or gold? Okay, well, in gold, I have a sea of electrons that are free to move around, whereas graphite is carbon, and the electrons are bound between the atoms of carbon. So I'd imagine that graphite would have a higher resistivity, higher resistance to the flow of charge than gold, okay? And it does, okay? So graphite is not as good a conductor as gold because it has a higher resistivity. So I'm going to teach you guys how to calculate the resistivity of different materials. You can go online and you can get a whole table of different resistivities, and that's what electricians are going to do. They're going to find materials that have an appropriate resistivity for the job. Okay, so here's a formula for resistance. We had Ohm's law, which is how I measure it in the lab. Okay, but here's another formula that describes the resistance of a material based on certain variables. So this rho, which looks like the density symbol, in this case, that symbol is resistivity of the material. L represents the length, okay, so that length of the material. And A is the cross-sectional area. What that means is if I take a look at this wire, the wire looks something like that. And if that's the radius of the wire, then pi r squared is my cross-sectional area of the wire, that whole area there, okay? Now, what does that have to do with it? Well, the charge flows in that area. So we can imagine if I make the area larger, I have more space for that charge to flow. And that's essentially what resistance is. So if I have the resistivity of the material from a textbook, and I know the length of the material, and I know the cross-sectional area of the material, I can calculate the resistance, which I can then confirm in the lab using an experiment, okay? which you guys are actually going to do. Okay, so what are the units for resistivity? This is a common question. So just by looking at the formula, would you be able to tell me what the units of resistivity are in this formula? Okay, well, R needs to be measured in ohms, L is measured in meters, area is measured in meters squared. So how does this end up combining to end up being ohms? Okay, so what I can see is that this is going to be like, that's my units for resistivity over meters, because that meter and that's going to cancel out. So I need to be able to then cancel out, I need to cancel out that M to then get ohms in the end. So whatever units are here needs to cancel out the M and leave ohms. So I imagine that the units would be ohm meter, because that would allow me to cancel out the meters and leave me with ohms. So resistivity is equal to ohm meters, okay? That's the unit for resistivity, okay? How can we minimize resistance in materials? Well, the formula is speaking to us. If I want to minimize the resistance, I need to look at how the variables are related. Number one, I want to find a material that has low resistivity. Number two, the resistance is directly proportional to length. That's what this formula is saying. So if I make the length very, very small, so instead of using a long wire, I use a very, very short wire, okay, that's going to have a less resistance. So the smaller the wire, the less resistance it's going to have. But also what I want to use is a very large diameter for a very short wire, okay? The larger the diameter, the greater the cross-sectional area, okay? The greater spots, the more charge carriers I'm going to have, the more space for that charge to flow. You can think about it as a highway. The more lanes I have for electrons to flow, the faster it's going to flow. If I make it small, I have less lanes, and you'll get a bottleneck in the traffic, okay? Increasing the cross-sectional area, decreasing the length will decrease the resistance. Okay, so here's just a sample problem before we end this. How would I calculate the resistivity of a material? So calculate the resistivity of a 10 centimeter wire that has a diameter of 1 millimeter and transmits 1 ampere of current when 9 volts are applied. So first I'm going to write down the resistivity formula. Okay, and I'm going to rearrange it. So I'm trying to get the resistivity. So if I rearrange it to isolate resistivity, it looks like this. Okay, so now I figured that out, but nowhere in this problem does it tell me resistance. I can figure out the cross-sectional area and the length, but nowhere does it tell me the resistance. But it does tell me the voltage and the current. So what I do know is resistance is equal to voltage divided by current. So I can then make the formula voltage divided by current, which is my resistance, times pi r squared, which is the cross-sectional area, divided by 0.1 meters, which is the length of the wire, will be equal to my resistivity. Okay, so if I plug everything in, 9 volts divided by 0.1, oh sorry, not 0.1, by 1 ampere, okay, times pi times, okay, is that the diameter? Oh, it's the diameter of the, yeah, the diameter of the wire is 1 millimeter. So another way of doing that, so 1 millimeter, so 0.0005 meters would be half a millimeter diameter, or not diameter, half a millimeter radius squared, divided by 0.1 will give me the resistivity. So if we figure that out, put it all in our calculator. Okay, here we go. So 9 times 3.14 times 0.0005 squared divided by 0.1 gives me a resistivity of 7.1 times 10 to the minus 5 ohm meters. Okay? And that's about right. That's roughly in the range of many conductors that we have. That would be a highly resistive conductor, such as nichrome. All right, we're going to be doing a lab this week by measuring the resistivity of a conductor. Mr. Phillips is going to help us with that. And that's a required lab that we're able to measure the resistivity of a wire. Okay, so you're going to try to do that on Pivot with us and Mr. Phillip. Okay, thank you.